For centuries, maybe even longer, people have gazed up at the moon. They saw its craters and shadows. Some imaginative folks joked that it was made of green cheese. It is a fun idea. It makes for good stories and cartoons. But as a scientist, I have to tell you, the evidence just isn't there. We have looked at the moon up close. We have sent astronauts there. They brought back rocks. None of those rocks were cheese. They were basalt and anorthosite, which are types of volcanic rock. So, we can put that delicious myth to rest. The moon is a world of rock and dust, not a cosmic dairy product. So, if it's not cheese, what is it made of? For a long time, the moon kept its biggest secrets hidden deep inside. We knew about the crust, we knew about the mantle, the layer beneath the crust. But the core, that was a cosmic mystery box. Did it have a core at all? Was it liquid? Was it solid? Scientists had theories, of course. They made educated guesses based on the moon's density and how it wobbles in its orbit. These clues suggested there was something denser at its center. But getting a clear picture of something buried under hundreds of miles of rock is incredibly difficult. It requires some clever scientific detective work. The journey to understand the moon's core didn't start yesterday. It began with the Apollo missions back in the 1960s and 70s. The astronauts didn't just collect rocks and plant flags. They also set up scientific instruments. One of the most important sets of instruments were seismometers. These devices are like a planet's stethoscope. They listen for vibrations or moonquakes. These quakes can be caused by meteorite impacts or by the gravitational pull of the Earth. By studying how these seismic waves traveled through the moon, scientists got their first fuzzy glimpses of what might be lurking in the deep interior, hinting at a small, partially molten core. Now, fast forward to today, November 15th, 2025. We have much more data and much more powerful computers. A team of scientists, led by Arthur Briaud, recently revisited all that old Apollo data. They combined it with modern information about the moon's shape and gravity field. Using sophisticated computer models, they were able to process the signals with incredible precision. What they found finally gives us a clear answer. The echoes from those long-ago moonquakes have finally solved the mystery. The moon doesn't just have a core, it has a core within a core, much like our own planet Earth, which is a truly remarkable discovery. The big news is this: the moon has a solid inner core. This is a huge confirmation. For years, scientists debated whether the innermost part of the moon was liquid or solid. These new findings show a solid ball at the very center. It is made of metal, specifically an iron-nickel alloy. What's really fascinating is its density. The models show that this solid inner core has a density of about 7,822 kilograms per cubic meter. That number might sound random, but it's incredibly significant. Why? Because it is very, very close to the density of iron and nickel here on Earth. This is a powerful piece of evidence supporting our theories. So how did they figure this out? It all comes down to seismic waves. Think of it like this. When a moonquake happens, it sends vibrations traveling through the entire lunar body. Some waves travel straight through, while others bounce off different layers. Seismometers on the surface record when these waves arrive. Waves that pass through a solid material travel at a different speed than waves that pass through a liquid. By carefully analyzing the travel times of all these different echoes, scientists can create a map of the moon's interior. It is like using sound to see what is hidden deep beneath the surface. This new study confirmed the presence of a liquid outer core, which is about 362 kilometers, or 225 miles, in radius. This liquid layer surrounds the newly identified solid inner core. The solid core itself is estimated to be about 258 kilometers, or 160 miles, in radius. So, the entire core system is about 5% of the moon's total mass. This might sound small compared to Earth's core, which is about 30% of our planet's mass, but knowing these dimensions is crucial. It helps us understand how the moon formed and changed over billions of years. The technique used here isn't new, which is what makes the findings so credible. We have been using seismology to study Earth's interior for over a century. That is how we discovered our own liquid outer core and solid inner core. By applying these same trusted methods to the data from the moon, scientists can be confident in their results. It shows the power of the scientific method. We take tools that work well in one place and apply them to new cosmic questions. This confirmation gives us a solid foundation, no pun intended, for understanding our nearest celestial neighbor. Now, you might be thinking, a solid iron core, a liquid outer core. So what? Well, this discovery is a huge clue in solving another major lunar mystery, the Moon's ancient magnetic field. Today, the Moon has virtually no global magnetic field to speak of, but when we look at the oldest lunar rocks, the ones brought back by the Apollo astronauts, they show something amazing. They are magnetized. This means that when these rocks first cooled from molten lava billions of years ago, they were in the presence of a strong magnetic field, one that might have been as strong as Earth's is today. Where did that magnetic field come from? A planet's magnetic field is usually generated by something called a dynamo. This happens when you have a rotating, convecting, and electrically conducting fluid. In simple terms, you need a churning, spinning liquid metal core. For a long time, scientists were puzzled about how the Moon's small core could have powered such a strong dynamo. Some theories suggested that big impacts could have temporarily stirred up the core, but the evidence of magnetism lasts for a very long time in the rock record, suggesting a more stable, long-lived source was needed. The discovery of a solid inner and liquid outer core provides a beautiful explanation. This structure is exactly what you need for a dynamo, but there's another piece to the puzzle, called mantle overturn. The idea is that early in the Moon's history, dense materials in the lunar mantle, rich in titanium and iron, slowly sank down towards the core. As this heavy material sank, it displaced the lighter liquid of the outer core, forcing it to churn vigorously. This powerful churning of the liquid iron is what would have generated the strong magnetic field that magnetized those ancient rocks. Eventually, this process slowed down. The mantle stabilized and the churning in the core subsided. The dynamo sputtered and died. The Moon lost its global magnetic field, leaving only the ghostly magnetic signatures locked away in its oldest rocks. So, by finding this solid core, we have found the missing piece of the story. We can now connect the deep interior of the Moon to the magnetic history written on its surface. It paints a complete picture of a dynamic, active young Moon that was very different from the quiet world we see today. Understanding the Moon's core isn't just a piece of lunar trivia. It fundamentally changes our understanding of the Moon's entire life story. Knowing its structure helps us refine our models of how the Moon was born. The leading theory is the giant impact hypothesis. This idea proposes that a Mars-sized object named Theia collided with the very young Earth. The debris from this massive collision was thrown into orbit and eventually came together to form the Moon. Knowing the size and composition of the Moon's core helps us test and improve this dramatic origin story. This knowledge is also critical for future exploration. As we plan to send humans back to the Moon with programs like Artemis, we need to know everything we can. Understanding the interior helps us predict things like seismic activity or moonquakes. It also tells us about the distribution of resources. The process of mantle overturn, driven by the core's evolution, would have affected the composition of the entire Moon. It helps explain why certain elements are found where they are on the lunar surface. This information is vital for planning where to land, where to set up long-term habitats, and where to search for resources. Furthermore, the Moon serves as a time capsule for the early solar system. Because it has no atmosphere and very little geological activity today, its surface preserves a record of conditions from billions of years ago. By understanding its internal evolution, we can better interpret that record. The Moon's history is tied to Earth's history. Studying the Moon's dead dynamo helps us better understand the dynamo that is still active inside our own planet, the one that generates the magnetic field, protecting us from harmful solar radiation. The Moon is a scientific stepping stone to the rest of the cosmos. So the next time you look up at that beautiful silver disk in the night sky, remember what's inside. It's not cheese. It's a complex, layered world with a story to tell. Deep beneath the silent, dusty surface lies a solid iron heart, surrounded by a once-churning sea of liquid metal. It's a testament to a dynamic and violent past. And by listening to the faint echoes from its deep interior, we have finally begun to read the opening chapters of that incredible story. A story that connects us to our own origins and our future in the solar system. Keep looking up.